Okay, welcome everybody to our PSI seminar for July 23rd. I'm pleased to welcome Stephen Hill, who is joining us today, and he is going to talk about a new optical method to observe Jupiter's clouds and composition. So, Stephen, welcome. Thanks for being here. And if you want to go ahead and share your slides, I'll let you take it from here. Yeah, are you muted, Stephen? Yeah, you're muted.
There we go. All right, are you seeing the slides?
Yes, looks good.
All right, terrific. Good morning, and thank you for the opportunity to give this seminar. As Amanda said, I'm going to be talking about a new optical observing technique that I developed and Pat Irwin validated and refined. And so first I'll talk about some background and motivation, kind of at a general level. Then I'll present the basics of the band approximation method that I developed. And from there, we'll look at validation through a comparison to formal retrievals using VLT MUSE data and the Nemesis retrieval code. I'll also provide some examples of applications using small telescope data, and then I'll wrap up. So let's jump into the background. So why is Jupiter and why are its clouds and composition so important? First of all, Jupiter is the archetype of a giant planet, both in our solar system and among exoplanets. It's really key to understanding how these kinds of planets function. It also provides a natural laboratory for investigating circulation, convective processes, and storms on fluid planets. And its bulk composition can shed light on how the solar system formed, what elements are enriched, which are depleted, and basically the processes by which the solar system formed. Ultimately, the upper weather layer is coupled to the deeper layers of Jupiter, so we can use upper level observations to infer conditions at depth and get at those sort of compositional pieces of information. And then, of course, there's a lot more, but it's only a hour-long seminar. So I'm going to focus on the upper layers, the cloud composition, the cloud altitude, and the method that I developed. There's a long history of using thermochemical models to determine the expected cloud heights and compositions on Jupiter. Typically, these are equilibrium cloud condensation models, or ECCMs. Given what we know about Jupiter's composition, temperature, and pressure profiles, these models predict three main cloud layers. Of course, there are a lot of other complex processes going on. Some of these lead to hazes at various levels, as well as coloring agent or agents that also must be considered. The three main levels are typically seen as ammonia, ice at about 0.7 bar, ammonium hydrosulfide at 2.5 bar, and water or a water solution at 5 to 7 bar. The ECCMs, the models, are usually static or quasi-static 1D models, but real-world Jupiter is much more complex. The details of where the clouds are is affected very strongly by dynamics and the resulting transport. And here we see kind of a cartoon that melds a lot of the current ideas about what the upper layers actually look like and how they're distinct in convective systems, deep and extended convection on the left-hand side of this figure, and then sort of the standard cloud layers of water, ammonium hydrosulfide, and ammonia ice. And then on the right of that heterogeneous cloud figure, you've got sort of the dry locations that show maybe still there's some condensates or aerosols, but much thinner. In addition to this sort of complex process that occurs above about 20 bar, which is the figure from the last page and on the right here, microwave sounding and radio sounding has been used to penetrate much deeper into Jupiter down to about 100 bar. And what we see is a lot of asymmetry on the large scale. This is from Guillot et al., a latitudinal slice through the atmosphere and the ammonia abundance there. And what we see is this asymmetry. We see the equatorial zone strongly enhanced, very deeply strongly enhanced. We see the north equatorial belt depleted in ammonia. And we also see some subtler features vertically where there are local minima and maxima that imply a deeper convection. So how do we remote sense Jupiter's atmosphere? Basically, it's all about contribution functions. And these are essentially weighted functions that are based on sort of a hydrostatic atmosphere assumption and the profile of the gases, aerosols, and other components that might be seen at certain wavelengths. So on the left here, you have the optical and very near infrared contribution function. So you can see that the 890 nanometer band there sees very high in the atmosphere. That's the prominent, well-known methane band that's observed. But in the continuum in red, we can see much, much deeper past 2, 3, 4 bar. And then you've got the microwave and radio on the right, which do have overlap with the optical. And again, I've offset the images so you can see that, but they also probe more deeply. And so we see that, but these different means of sensing are looking at different kinds of things. In the optical, you're looking at aerosol reflection and scattering, Rayleigh scattering, and gas absorption. But in the radio, you're looking at emitted temperature and ammonia absorption is affecting and actually kind of creating a degeneracy with the sensed temperature. So you have to reconstruct that. And of course, we also have point measurements that are kind of the gold standard. Entry probes, obviously the gold standard, and occultations are also very useful, but they do not provide you the global coverage. So kind of in short, the atmospheric processes are very complex. The measurement complexes are, in fact, rather challenging, and different kinds of observations only partially overlap in the parameter space. Some are sensing temperature, some are sensing ammonia, some are measuring aerosols, some are contaminated by aerosols. So it's a real challenge, and reconciling the models to observations is challenging. This is an example of a survey of relatively recent retrievals of cloud heights based on a combination of modeling and observations. And what you can see here is the range of deep, sort of the thick, optically thick and physically thick extended cloud layers has a huge range of base pressures that range from as deep as about 5 bar, which is where the water cloud is, to a base at about 0.7 bar, which is where the models show an ammonia ice cloud should be. In addition, you have thinner but physically extended hazes in the light gray, and you have proposed chromophore or coloring agent layers shown in orange. So this is just showing the amount of ambiguity that goes on in a general cloud retrieval. They have consistency very broadly, but there's a lot of open questions that still remain. And so some of the questions that are particularly interesting to me are, at what pressure are the optical clouds on Jupiter, and what are they made of? What processes explain the behavior of the North Equatorial Zone hotspots, plumes, and ammonia enhancements? What changes occur in cloud pressure and ammonia mole fraction during weather events? These can be local events that are convective storms, or global events or near global events like equatorial zone disturbances. And how are deep atmospheric ammonia variations and the upper weather layer coupled? So let's move on to discuss the band approximation method and how it might address some of these questions. So if we kind of look at the theory here, we're going to use methane as a benchmark for ammonia. And this simple cartoon is going to illustrate that. Basically, if we use weak optical bands, we know that the light will penetrate to the main cloud deck. As we saw from the contribution functions earlier, we get down to a couple to a few bar in the atmosphere. What we've got is methane has a uniform mole fraction distribution in the atmosphere, and that's just kind of the green overlay there. However, ammonia condenses out with altitude. Whether or not it's forming thick and notable ammonia ice clouds is another question, but it definitely reduces its concentration as it goes up and hits that condensation altitude. And it varies with location because it's caught up in circulation. So there are upwellings and subsidence here shown where the convection is active, and then downwelling where the dry locations are. So we can use methane as a fiducial, as a benchmark for determining the ammonia abundance. And that's kind of the inspiration for this method. This is sort of your basic geometry. I assumed the simplest possible atmospheric and cloud model, a reflecting layer model. This assumes that a cloud's basically almost like a solid object that has a discrete reflecting top and no physical depth, so you're not dealing with multiple scattering. This allows you to deduce the gas absorption, methane and ammonia, above the cloud, just knowing the geometry and key gas parameters. So you basically have the path length here, which is a function of the incident and emitted zenith angles and the vertical depth of the clouds in the atmosphere. You can get the optical depth then from the physical parameters, the absorption coefficients of the gas, scattering cross sections, density of the atmosphere, and then you get the incoming light versus the reflected light. And that's basically how you tell and spatially differentiate where you've got more and less absorption. So I had several years ago taken a very simple objective grading spectra of Jupiter and found that it compared well with published work. And, the deep ammonia band that we're used to at 889 nanometers is extremely evident there. And of course, that's the kind of picture that we're used to seeing with these high hazes over the Great Red Spot and the equatorial zone and the polar regions. However, weaker ammonia and methane bands are also clearly seen both in the published work and in my measurements of the spectra. And I thought to myself, with band depths of 5 to 15% on these two bands here, seen at 619 for methane and 646 for ammonia, that would be plenty of signal for careful filter observations. And it turns out that Comson and Krenez back in the 1970s, along with some others, had worked with these bands using slit spectra, but their intention was to primarily estimate the bulk carbon and nitrogen abundance of Jupiter, as opposed to kind of looking at the weather layer in detail. But I wondered, had anyone tried imaging Jupiter in an ammonia band? And per the search I did not turn up anything. So I think this may be the first time this kind of measurement, at least in these bands, has been made. So how do we create methane and ammonia images? Basically, we first start with reflectivity images of Jupiter in 4 filters. We have the in-band filters for 619 and 647 nanometers in methane and ammonia, and there's a slight discrepancy. The 1 nanometer discrepancy is just the band center versus the filter center that I was able to obtain. And then we have continuum filters at 632 and 656 nanometers. And you can see in the top panel here, the shaded region in pink and blue are the actual amounts of light absorbed in those in-band filters. These filters are, and these bands are especially good to use because they have non-overlapping molecular absorption coefficients. So they're truly independent there. There's no sort of deconvolution or fitting that you have to do there. They also have similar wavelengths and similar band depths, which are key criteria. You can know that they're penetrating roughly the same depth into Jupiter's atmosphere. They're staying sort of in the linear region there of equivalent widths. And also, they're close enough in wavelength that you can, to first order, ignore any effects of the colors of the clouds, of the reflecting clouds that you're looking at. So what do we actually compute? By the way, these the images of Jupiter's here are actually ones, they're real data that I took. And I don't do any sharpening of the images because I don't want artifacts. That's why these look blurrier than maybe some of the other small telescope images that you've seen of Jupiter. There's no sharpening, there's no active or adaptive optics going on here. So to compute transmission, we just take the in-band images, the radiance images in methane and ammonia, and divide them by the appropriate continuum images. I actually, for the continuum image used for ammonia, it's actually an interpolation of both the 656 and 632 continuum bands because there's slight contamination from a methane band around 656. The 668 methane band contaminates the 647 nanometer ammonia band and the continuum band. Let me jump back there a second. So I use a interpolated value there just to get rid of that contamination. And also we can compute equivalent width as a useful tool, and we'll see that a little bit further in the analysis. For cloud pressure, It's pretty much a simple matter of taking the methane opacity, which is just the natural log of the transmission, and multiplying it by some key physical parameters attached to a basic atmosphere model. So you basically are including the mean molecular weight, the gravitational acceleration, Avogadro's number, and the methane absorption coefficient. And then we assume 2 for an air mass factor, that is the light going once through on its way into Jupiter and then outward after reflection. And then you can compute the ammonia mole fraction as a ratio between the ammonia opacity and the methane opacity multiplied by the ratio of the methane and ammonia absorption coefficients, and then referred to the methane mole fraction. And again, these are actual data, so you can see kind of the amount of detail you can see. You can also see a few artifacts in there because, of course, data are not perfect. But it demonstrates the fact that it actually works with data. So observations. How was this data taken? I used a Celestron 11-inch telescope on a commercial mount and a commercially available Planet video camera from ZWO, a Starlight Express filter wheel. So these are all basically available to amateurs. But I had to reach out to Edmund Optics and buy a few custom filters there. They have 10 nanometer wide filters that will fit in a 1.25-inch filter cell, and you can buy them for a reasonable price. This is why it's accessible to, amateurs who are willing to invest a little bit. So I had to buy 3 specialized filters there, and then I used a standard astronomical H-alpha filter for the 656 continuum. And then I used Sharp Capture software for video capture, and automation. So what does an observing sequence look like? Well, on the top there, sort of in the blue, you can see that I'm nesting the images that are the science data. I take the continuum images both before and after the in-band images, and then I take a methane in-band image before and after the ammonia images, and then I take the ammonia images centered. And by doing this nested imaging, I both increase the signal to noise by having 2 videos of each band, but also it minimizes rotational offsets, because once you rotate the videos to the central meridian of the central observing time in this window of observation, you've got symmetry both on the before and after center time images. And so it works out better that way to minimize the offsets. And then I also take context data, IRGB videos for science data interpretation. So there's a total of 11 videos per observation, which takes about 20 minutes to complete. What that means is I can get, during opposition, can get about 20 observations per night near opposition. And that typically is somewhere between 0.7 and 0.8 of a Jupiter rotation per night, which is really pretty incredible coverage. So for data reduction, I also use COTS software packages. And you can see what those are at the bottom there. These produce radiance images, transmission and opacity images, and cloud pressure context and ammonia mole fraction images. And this array of images is a standard data product that actually I have posted now on GitHub. So it's a standard product, and I have it for all of my observations. How do I analyze the results? That's all done with custom Python code. I use Planet Mapper, NumPy, Matplotlib, and we look at meridional profiles of absorption. And I know this is perhaps a little bit small, but there is a plot there, spectroscopic plot of a meridional profile from Teifel et al. 2018. That's light gray in the background. And you can see that the various observations from the SCT, Schmidt-Cassegrain telescope, that's my telescope, and some VLT MUSE data agree pretty well with that. In addition, we can look at the mole fraction profiles, and again, with latitude, the variation there follows the pattern of mid-infrared data from Fletcher et al. And then we also make maps. So there are great red spot images, and these confirm the ammonia depletion seen in the top by Gemini, Texas, that's again Fletcher et al. That's I think a different Fletcher et al. Paper actually, but it's in Hill et al. At the bottom. Basically, there's a lot of depletion at and south of the Great Red Spot. That's a 500 millibar measurement. And if you look at VLT MUSE data that Pat Irwin provided to me to apply the method to, you can see the depletion. It's mostly centered on the Great Red Spot with a little bit more depletion to the south of the Great Red Spot. And coincidentally, serendipitously, I was actually imaging Jupiter only an hour later from that VLT MUSE observation. So you can see that single observation taken on September 19, 2022. It shows the major features that are seen in the VLT MUSE data in ammonia, including the depletion around the Great Red Spot, some of the enhancements to the north and to the east of the Great Red Spot, as well as a little bit of that depletion there that's in right on the eastern edge. So it's obviously a lot noisier because my telescope's a lot smaller than VLT MUSE, but this was a real confidence builder. So let's look at building more confidence. What do formal retrievals have to say about validation of the band approximation method? So first of all, I wanted to try and get independent verification. Even though we had good positive results, before I had the VLT data, I was concerned that there might be something funky with my processing, with my observing, with my system, with my camera, with my flats. So I really wanted to have independent verification, a different instrument system, different processing codes, and see if we get the same results. And it would be nice to use a bigger telescope. So enter Pat Irwin from Oxford with assistance. John Rogers through British Astronomical Association connected me with Pat, and we got data from a somewhat bigger telescope, which was really, really interesting and fun for me. So the VLT MUSE observations of Jupiter are really made in support of Juno, and they're focused on the various perijoves that spacecraft sees. The animation on the left shows that MUSE is a spectral imager, so it has fine resolution, and you can watch this, the black and white image there change subtly as it goes through the different areas of the spectrum. And basically it covers from 475 to 933 nanometers with a spectral resolving power of about 4,000. So that's really great data. And it takes, exposures are a few seconds, which is just super cool. Data are smooth and stepped for compatibility with methane absorption coefficients, and that's to ease analysis. And then there's data available almost every year from 2014 to 2023. Another tool that Pat developed is Nemesis, the nonlinear optimal estimator for multivariate spectral analysis. And this was developed for solar system studies and extended to exoplanets. It's basically a retrieval code for atmospheric composition and vertical structure. Generally applicable to any planetary atmosphere, it handles thermal emission as well as multiple and single scattering, and the core retrieval code is based on optimal estimation. It can analyze VLT MUSE spectra to retrieve maps of cloud opacity as well as ammonia abundance, and this has been done by, for example, Irwin et al., Broad et al. So it's been around and it's been used. It's well respected. It is accurate but slow, and it's slow because it has to handle the computationally intense multiple scattering calculations. This limits it to latitudinal averages or a few interesting regions. It does find high ammonia in the equatorial zone and low ammonia in the north equatorial belt. But introducing the method that I kind of developed and is consistent with the old spectral and Krenes and Combs method, a simple method, a backyard telescope, together they achieve similar results. So Pat, as a first step, took the spectrally resolved data cubes from VLT MUSE. He created synthetic images by convolving those spectral images with the throughput, with the transmission filter profiles of the filters that I was using. From these, he then created radiance images, and from that, he was able to, replicate transmission, opacity, and ultimately the pressure and ammonia abundance using VLT MUSE data. So the results he got were similar to my results from 2024, but he used a nadir air mass factor of 2, which gave a cloud level deeper than what I had obtained in that paper. He got 2 to 3 bar. I had used eta equals 4, which is valid for a disk integrated spectral measurement and really wasn't the best thing to use when I was doing my spatially resolved measurements. So the air mass factor of 2 is the appropriate one to use there. So the question then comes up, how far down are we really seeing? We're seeing, we think, 2 to 3 bar, but the clouds on Jupiter are made of ammonia ice, right? At least that's sort of the traditional view, and they should be at about 0.7 bar. Well, what Pat did in Irwin et al. This year publication is he looked at the actual ammonia profile at and above zero point 0.7 bar, which whether or not there are optically thick clouds created from ammonia, there's definitely got to be condensation going on there and a great reduction in ammonia with decreasing pressure, because that is what the measured temperature profiles show. He then computed two-way transmission spectra, and that was calculated in a standard aerosol-free atmosphere, but included Rayleigh opacity. And then he computed equivalent widths of the bands for ammonia and methane as a function of pressure. So again, a little bit small, but the pink is the methane ammonia width as pressure, as you go deeper in pressure, and the blue is ammonia. The actual measured equivalent widths for ammonia and methane are 2.2 and 0.8 nanometers respectively. Those are represented by the vertical dashed lines. And if you look at where the vertical dashed lines intersect the curves, the predicted curves, what you find is that that is consistent with cloud tops at 2 to 3 bar. So we've definitely got evidence of, clear evidence of seeing the main cloud deck being at about 2 to 3 bar. What else can we use to support this? If we look at center to limb variation, then we can have some expectations based on this reflecting layer model. If we have a reflecting layer model, then at the limb we expect to be looking through more atmosphere, so we expect there to be more gas absorption and equivalent width to increase linearly with air mass towards the limb. A MUSE zonal profile was taken along the equator about plus and minus 1 degree, and it shows that the equivalent width decreases with increasing air mass. So this essentially invalidates the reflecting layer model, which was a simple beginning tool, and shows that the aerosols are in fact vertically extended, which is a real-world expectation. But in addition, it shows that the ammonia equivalent width drops faster than the air mass than the methane equivalent width does. So that's another interesting piece of information. You can plot the ratio of the equivalent widths, and you find that they are somewhat linear there. And the slope of this ratio of equivalent widths is another way of determining the sounding level. And our result is again consistent with 2 to 3 bar. So we're building up the evidence here, making the case that the main clouds reflecting on Jupiter are in fact deeper than we expect ammonia ice clouds to be at. So just to recap, the clouds appear deeper than expected at the ammonia ice condensation level. This is consistent with the conclusion of many previous studies. There are actually quite a few of them, so rather than citing them individually, the introduction to Irwin et al. Contains a very good review of those references. Spectrally identifiable ammonia clouds have been detected on Jupiter. However, they're typically localized and usually associated with active convective systems. So while those measurements can be made, they're a little bit challenging. And in fact, they are not seen except in localized regions, as far as we can tell. This study here using the band approximation method is particularly compelling evidence for these deeper clouds, as the evidence is easily seen and comprehended. There are not a lot of degeneracies. Well, there aren't really any degeneracies. It is very straightforward physics, and it's a simple method. So this is a strong piece of evidence that clouds are a little bit deeper. So now the question is, what about the retrieval of gaseous ammonia profiles, and what are we seeing at depth? It seems, judging by how deep the methane band is seeing, that we're actually looking as deep at ammonia as maybe only was previously achievable with radio and microwave measurements. So let's look at first comparison of ammonia retrievals using the band approximation method to an actual full nemesis retrieval along a meridional profile, a latitudinal profile. So nemesis was fit to the spectra between 600 and 680 nanometers. The band approximation values, as you see there kind of at the bottom of this panel, as well as the purple is another method that's a variation on that Pat worked on, show the same latitude dependence of NH3, but it's too small compared to the nemesis retrieval by a factor of about 1.5. Why is that? Well, we need to account for the ammonia variation with height by applying a pressure-dependent scaling factor. I'll go into that a little bit in the next slide or two. What we find, that actual top panel just changed. It's now showing that pressure-corrected version of the Hill method and the FIT method that Pat developed, and it has remarkably consistent values with formal nemesis retrievals, both in shape and in quantitative value. And then these are kind of the same pictures that I showed earlier, but with the pressure correction applied to the ammonia. So the ammonia scaling factor, where does that come from and how do we compute it? Basically, the column abundance ratios we saw because the ammonia drops off above 0.7 bar because it condenses out. So the column ratio approaches a constant only at high pressure, but as we move up towards the condensation level, it decreases rapidly. And you can see that in panel D here, the middle one on the right, how ammonia drops off when you get starting around, a little bit below 1 bar and a little bit below 1 bar, I guess is what I want to say. And the methane is just a straight line. So what you can do is you can look at that column ratio and you can see the different column ratio there, the ammonia over the methane in panel E, and then we compute a scaling factor based on that. This pressure dependence correction factor or scaling factor is needed to match the deep ammonia abundances from nemesis retrievals. Basically, what we're doing is we're saying that when you're looking at ammonia instead of methane, there's an extra weighting factor that means you're looking deeper because the ammonia is depleted at the higher altitudes at the lower pressures. So this is basically a straightforward way of weighting it based on a computation of the column abundances. And it is based on a model, so there are some assumptions that go in there, but it's a fairly straightforward, just thermochemical model that shows that there will be condensation, but doesn't say anything about cloud formation specifically. If we move on to microwave and radio data, we can find that the band approximation latitude variation of ammonia is remarkably similar to deep variations of ammonia seen by Juno's microwave radiometer. VLA observations at 8 to 10 gigahertz probe 1 to 2 bar, and they are also very similar to the band approximation result. That's what's shown below on the right, and the band approximation result is shown on the left. The dark areas are regions of high ammonia abundance, so you can really see that sort of matching at the equatorial level, really the northern side of the equatorial zone. And then we can do more detailed comparisons with microwave radiometer on Juno and with VLA. Chris Mockel did a comparison, did an analysis that actually used them independently and combined. We see that the behavior is very similar with latitude. The variations are very similar, but again, we find a scaling factor. This is a different scaling factor of about 1.6. So that's a discrepancy that's still being investigated. And then this was another opportunity for me to present just the fact that there are variations with pressure vertically across all the latitude zones where there's a local minimum here seen in this retrieval by Lee et al. On the bottom left here. So that's an interesting thing that may be of impact and of interest to the band approximation method. So what are some applications? I'm going to show applications that have to do with the data that I've taken from the small telescope that I use, First of all, I now have data consistently, enough data that I stitched together maps. And basically, at every longitude on these maps, there are really 5 to 7 individual observations that have been stacked and averaged in a weighted average based on their distance from the central meridian. And there has also been an empirically determined limb correction applied to ensure smoothness. So these maps here were synthesized from 24 individual observations. So that's 24 times 20 minutes. So that's a lot of observing time. And the color tables that I'm using here and that I'm using generally are used to leverage visual cues from moisture and clouds in terrestrial weather. So they kind of have a time-tested use in selecting these color tables. And what you see in the top is the ammonia abundance or mole fraction, and the bluer and greener areas are the sort of, more humid areas, so to speak, where there's more ammonia, and the drier areas have the sort of deserty colors, white and brown. The middle panel is the cloud pressure in millibars, and basically there you see where the clouds are high, they are light, bright white, and where the clouds are deep, there's sort of clear areas in the high clouds. You're looking down through so-called blue sky. You're not obviously seeing no clouds, but the clouds are much deeper there. And then, of course, you have on the bottom the context image. Oh, I should note that the mapped ammonia here does not have the pressure correction applied. And that'll be the case for everything I show here. So looking at a single Jovian rotation here, or a single map, I put it on an animation. We can see the great red spot, and on the left, we have depletion in ammonia there, and we can see it's a relatively high cloud region there on the limb in the cloud plot on the right. We also see hotspots, which are identified as deeper cloud regions on the cloud plot and in the context image. Same thing with plumes, except those are the bright areas. And then we take enhanced ammonia areas are seen as the sort of blue concentrations in the equatorial zone on the left plot. And then we have the sort of mysterious lavender thing in the middle of the equatorial zone, which is pretty atypical, but probably has to do with the ongoing equatorial zone disturbance that was happening in 2024. And then we can actually go ahead and watch this rotate. And what we're seeing is, a lot of the details near the equator where you've got low zenith angles. We've got higher quality data than near the poles, but you can still see features like higher clouds or aerosols near the poles, depleted ammonia near the poles. And right now you can see the South Equatorial Belt outbreak passing the meridian and now kind of rotating off. And we were able to do some analysis on that, at least a cursory first look. But you also see that we have some artifacts that remain, such as that dry zone south of the Great Red Spot is unlikely to be real. So there's improvements that can be made to the quality of the data. So sampling of features and results, we can track features such as that South Equatorial outbreak. We can look at hotspots and plumes and the complexes around them. And we can look at the Great Red Spot. The little boxes on those map patches represent analysis areas that we'll talk about in the next couple slides. So we can use those little boxes as regions of interest. And when we look at regions of interest or create map patches from stacks of maps, we also look at the standard deviation to know that there are no outliers, there's no huge statistical variations. And then we compute the statistics within each region of interest and their variation over time. And the variation over time here is shown for the regions of interest on the previous chart, and you see some significant deviations, and those are likely systematic errors because they're exceeding what I have for the statistical areas of the individual map patches. And so while there's physical variation that we probably can capture, right now it looks like there's a lot of systematic error in there as well. The regions of interest generally show increasing ammonia with increasing pressure, which is what we expect, or is it? So that goes back to the ammonia condensation level happening at about 0.7 bar, but here we're looking at about 1.7 to 2.2 bar. And what's going on there? We should be well below the condensation level. So unless there's transport and other processes that are resulting in replenishment of ammonia or concentration of ammonia at deeper levels, we really shouldn't be seeing that kind of slant. And we also notice that there are a couple points, such as the Great Red Spot wake in the South Tropical Zone, that seem to lie a little bit off of a general trend line there, and that might be interesting. So we want to use this to try and shed some light and investigate the vertical ammonia gradients below the condensation level. We also looked at 5-micron correlations in the Great Red Spot region with data courtesy of Glenn Orton and Tom Omery. The ammonia data really doesn't correlate well with the 5-micron emission. However, the cloud pressure does correlate well. And in fact, if you change the color table to be the same color table as we use for the 5-micron radiance, the correlation is really pretty astonishing. There's definitely lower spatial resolution, but not only is the lower radiance at the Great Red Spot visible, a lot of other features around there are visible just at lower resolution because of the smaller telescope. Then we can look at this a little bit more quantitatively. We know that our optical band method is penetrating to greater than 1 bar. We also know that 5-micron emission is attenuated mostly by clouds at 1 to 2 bar, as shown in this plot, which is really focused on the Great Red Spot, but is assumed to be generally true, that that's where the major absorption is coming from. So if we actually do a correlation plot here, what I've got is the 5-micron radiance, and the overplot is the band average method cloud pressures. And then on the right, I've got a scatter plot there of radiance in log units and cloud top pressure, and we can definitely see a strong correlation there, although it does appear that there's a break and there may be 2 trends there, and trying to understand that will be very interesting and important. And so this is consistent with earlier work that Irwin did and others did that correlated near-infrared reflectance with the radiance in 5 microns. But here we're looking at the actual cloud pressures, not just another reflectivity. We can also look at large-scale weather events in 2022 and 2024. Here I'm plotting in the orange 2023 and 2024 is orange, blue is 2023. Pressure on the left, ammonia on the right. And what we can see is the results of the equatorial zone disturbance in 2024 showing a clearing of clouds, as well as the north equatorial belt expansion showing a clearing of clouds into the north tropical zone. But we also have this sort of curious global offset in ammonia, which may be a calibration issue. If we look at the differences between 2023 and 2024, ignoring the blue curve for now, because that's a prior year that has some noise in it. But if we look at the orange curve, what we find is the equatorial zone disturbance is really dramatic. It's a clearing of clouds, a lowering of the effective depth of the top clouds by at least 200 millibars. We also see a localized increase in ammonia there. Same thing for the north equatorial belt expansion. And the offset, as I said, might be due to a calibration shift, and that needs some investigation. North equatorial zone, where's the ammonia? So we're moving into a new topic here. This is where, there's all this complex behavior with a potential Rossby wave that's equatorially trapped, creating these series of plumes and hotspots that repeat periodically in longitude. And what I've found using the band approximation method is the ammonia enhancements are found south of what are called north equatorial dark features. They're the visual equivalent of hotspots in 5 microns. This location is the same location as analysis of winds show that there's an anticyclonic gyre seen south of hotspots. And so this is compatible with other work and with the Rossby wave explanation. There's a couple references there, and there's a little bit of data that shows the relative locations of deep clouds or hotspots and enhanced ammonia regions. So if I want to track these regions, so I do want to track these regions to see what we can find. This is sort of a preview of some information I'm developing for EPSC in September. The features here show some unique clustering on the pressure ammonia plane. In particular, we have plumes show high altitude, low cloud top pressure at about 1600 millibars. The hotspots, or NEDFs, are deep in the clouds at 2000 millibars, 2 bars, and have a little bit more ammonia. But then the areas where the ammonia enhancements are and the gyres are has significantly enhanced ammonia and is at somewhat higher pressure, but not as high as the plumes. So what I'm positing is that we've got a cycle here as the eastward jet velocity carries, basically the phase velocity moves to the east. You've got a gyre which serves as an upwelling source of ammonia, which then is advected to the east-northeast because it's basically anticyclonic. So you've got spreading out of the material as it reaches high and forming a plume that trails off to the east-northeast. And then that eventually leads to the next hot spot where there's subsidence and clearing, and you end up with less ammonia. So that's work that's really current right now. So a quick summary and some future work. The band approximation method is affordable, accessible, and efficient. It's a great way to map cloud top pressures and the abundance of ammonia 2 to 3 bar in Jupiter's atmosphere. I have a quote here from Irwin 2025. For zonally averaged MUSE observations, we have seen that the simple Hill band approximation method yields determinations for ammonia abundance that are remarkably consistent with formal Nemesis multiple scattering retrievals. So that's a great plug. The method produces maps of Jovian ammonia that aren't so different from Juno microwave or VLA data, and it allows for detailed feature analysis from both BLT, MUSE, and from amateurs. And finally, the cloud tops are not at the ammonia condensation level, generally speaking. The bulk of the reflection is coming from deeper levels at 2 to 3 bar. Future work, I'm looking at trying to establish the band approximation method for ammonia and cloud pressure as a routine, well-calibrated and accessible observing technique for others to use as well. Establishing and sustaining collaborations with observing teams using large telescope facilities and spacecraft. Adopting and developing analysis and modeling techniques that integrate diverse observations such as mid-infrared or microwave and radio so that we can synthesize these analyses all together. And then my science focus is really on the vertical cloud and ammonia profiles, north equatorial zone phenomena, and convective outbreaks. And the chart I show here is sort of a progress chart. For the first couple years I was doing this, I was just trying to figure out if you could actually legitimately detect ammonia absorption from that 646 ammonia band. Second 2 years, I was developing the method to retrieve the actual ammonia mole fraction and the cloud pressure. And then last year, I automated a lot of systems, but not all of them. And at this point, I have close to 500 individual observations of Jupiter spanning 5 years, the bulk of which are, of course, in the last year. And if we do a little bit more automation, we can engage amateurs more and greatly expand coverage. And then finally, Mike Wong was intrigued by the technique from conversations we had back at AGU last year, and he submitted a Hubble Guest Observer program, the title, and it was selected. Found that out on Friday, and time was awarded. The title is Simultaneous Mapping of Ammonia on Jupiter with Juno and HST Wide Field Camera 3. We've got co-eyes of Boraker, Hill, Irwin, Rogers, Simon, Teifel, and DePatter. And we will be measuring ammonia spatial variation to address goals in atmospheric dynamics, chemistry, and origins. So we'll be looking at tracing vertical flows, looking at cloud chemistry, and looking at bulk atmospheric abundance. This will be the first ever use of the F645 nanometer filter on Hubble to observe Jupiter, and of course the first application of the band approximation technique I developed. And we've got 4 Juno parajoves of observing time on Hubble in cycle 23, and then 3 each in cycle 34 and 35. So this is incredibly exciting to me for something that I originally sort of developed outside of my my main avenue of work. And now here it is, it's developed into something that's rather fruitful. And of course, that only happened because of a bunch of other people making great contributions. John Rogers was sort of my first contact, and he being the Pro-Am coordinator extraordinaire at British Astronomical Association, helped connect me with Pat Irwin and Charlotte Alexander, who provided me with MUSE VLT MUSE data. And then, of course, that grew into a paper of their own, where Pat led. Lee Fletcher, who answered numerous questions I had that were just a little bit beyond my depth. Glenn Orton and Tom Malmry have been great in terms of collaborating on 5-micron data. And then Mike Wong, of course, who's picked up an interest, and we have the Hubble proposal with him. And then, are there any questions? That kind of wraps it up for me. I've got my contact information there, information for the key papers, and I should have put in there the GitHub location, but maybe I can post that someplace so people can find the browse data sets. And that is it. I'm happy to take questions.
Stephen, this is great stuff. Thank you so much. That's a
Thank
ton
you.
of stuff. I'm sort of there's a lot, I had a lot of questions and then you answered them. And so I'm like, I have some questions still, but I
Okay.
might,
All right.
it might be stuff that you covered and then I was losing track a little bit.
Yeah, it was a fire hose.
Yeah, but great. I mean, really great stuff. And congratulations on getting the Hubble time. That'll be really exciting
Yeah,
to get
absolutely.
even more data and utilize your method even more.
Yes, absolutely.
That's great. And one thing that I wanted to ask about though is with that and with the sort of advancing of this technique, and that you said can be used by more amateurs at these kind of accessible wavelengths from the surface of the Earth. What do you hope to gain from that then? More temporal coverage, spatial coverage, spatial resolution with different instruments or different facilities?
I think there are some specific benefits. One is better coverage. You know, while I had something like 300 observations last year, I missed some Juno perijobes just because I'm an individual. There's cloudy weather, even in Denver. And so
Okay.
getting that kind of coverage that correlates with professional campaigns, I think is really important.
Okay.
I think also having sort of the confirmation of observations at multiple independent observatories, you've seen that the small telescopes can be vulnerable to artifacts, and there are some, I actually have a couple challenging flat field effects to correct that keep recurring, and it's very frustrating. So each individual telescope is going to have its own minor impacts that you can kind of average out if you get more observations. And then the greater coverage is also going to provide you early warning of events that are occurring on Jupiter. For instance, are you seeing a convective event earlier than you would see visually because you're looking directly, you're measuring a cloud height change that might be subtle to see visually without looking in these specific bands? Are you seeing changes in ammonia that's actually going to be driving future convection? Or can you say predict what a equatorial zone plume is going to look like by looking at the evolution of the adjacent ammonia enhancement that's supplying the formation of that plume? What's the lag time there, for example?
Yep.
So you can't do that, and those are sort of moderate resolution things. Looking at getting more data, you can also then try to tie this data quantitatively to highly calibrated data like Hubble or like VLT MUSE. And I think that's essential because independently calibrating the small telescope data is challenging. I tried doing it with using the moons of Jupiter, and the statistical errors were just too big. So it's actually basically tied to MUSE calibration at this point.
Okay. Okay, great. Kat or Jeff, questions on your ends?
Well, thanks. Great talk. I will tell you, I have a Python package called Bernashev, which is what you want for calibration. Basically, it uses the Bernashev spectrophotometric catalog from 1985 or something like that. It's in Russian. Basically, I turned on to it by Boston University. They use weird filters like sodium and stuff like that. And so you look at the standard stars in the Bernashev that fit your brightness. There's a ton of stars, and then I have the code. I mean, you could do it yourself. That just takes his spectra, and you convert, or you just multiply by the band capacity of filters, which should be well determined by you.
Right.
Whoever, and boom, it gives you what the transmission is. Period. End of sentence. Of course, that doesn't include your telescope and all that stuff, but it does, right? Because it's so basically I use it for ratios, but it also gives the absolute as well,
Right.
because you have and so I've been doing these for I scripted in as part of my automated system, and then I've got hundreds, maybe thousands by this time, and I plot them as a function of time, and I say, yeah, my filters are happy and all that stuff. So calibration need not be a problem.
Okay. Yeah, I look forward to anything that helps me do better calibration.
Yeah. So, Kat, do you have a question?
Nope, I was just going to say it was a good talk. Too far outside
Yeah.
my expertise to have relevant questions, but thanks for the great talk.
Yeah,
All
no,
right,
thank you so much. I have a question still though. Jeff, did you have one?
I mean, I had one. It's about a potential future application collaboration, so it might be off topic. So go ahead and ask your.
Okay, mine is just to clarify, because this is not in my expertise, but I was following along and thinking that so I'm hoping you can just clarify this for me.
Yeah.
You were anticipating that because you're using shorter wavelengths than using the 619 rather than the 660, or sorry, the 889 that had been done a lot before, that you were going to be sensing less high in the atmosphere at the predicted at the predicted clouds or condensation at like 0.7 bar.
So
is that right? Or that
that's part of it.
But then you ended up sensing deeper.
Right.
At 2 to 3 bars. And I guess I wasn't fully grasping why that is.
Right. So basically, the contribution function for the 889 strong methane band really means that you can't see much below 200, 300, 400 millibars. And that's where there are high haze layers, and you're not seeing below that. So I expected using the shorter wavelengths, I would see below that, and the contribution functions show that you can see down to a couple to a few bar, okay, in an aerosol-free situation. Now, that means if there were clouds at 0.7 bar, I would see down to them because I'd see, well below where the 889 band sees. But in fact, the equivalent widths and the other, measurement show that I saw much deeper than that. Right. But it's because Jupiter was different, and I was using a different band than the 889. So my expectation was based on the cloud condensation models to see down to about 0.7 or 1 bar. And in fact, I'm seeing deeper because it's not there.
Right. Okay. So that's a really great result.
Yeah, I think so. Definitely think so. Yeah.
Okay, cool. Okay, Jeff, go ahead.
Yeah, and then to circle back, I mean, congratulations. This is really great to sort of hit the home run of Hubble from your back of the envelope calculations, which led to this method and everything like that. So and then find some weird stuff.
Thank you.
To boot. That's my talk at the retreat, which I guess you won't be at. Is like how can we support new instrumentation for stuff like this? Which in this case it's filters that aren't necessarily new, but and Kevin Gay is doing citizen science stuff, and so this applies. So you're applying to join a great team. But my question is, so you seem to be looking at this roiling and toiling atmosphere of people. Okay. These plumes and the hotspots and stuff like this. And I have been looking for a way to get more frequent monitoring on something like the temperature of Jupiter's way upper atmosphere, and it's ionosphere. So H3 plus is a way to do that.
Mhm.
And the reason for this is I have a hypothesis of what's affecting the plasma torus diameter. Okay, the diameter is not really supposed to change, and it does, and it could be Pedersen conductance if it's a magnetic effect. And if the change of that in the ionosphere could move the plasma torus diameter. I had this nice example of the torus growing, and I asked the Boston University group who gets data like that. Oh, yeah, no group got any H3 plus data that year. And
Hmm.
so here you have a mechanism for getting observations, 20 a night or something. Which this is the kind of stuff I do. Now it's not for H3 plus, and so there
Right.
need to be a little bit connected dots. Um, uh, and I wonder, that would be the endpoint I'm interested in to test my hypothesis. Is there some way of estimating sort of the temperature? For me, it would be in the, toward the polar region where Io's L shell hooks into the
Right.
planet. And so it's, because I know very little about Jupiter's atmosphere except it's there.
Right.
It makes belts and zones. So yeah, is there any way that you would know about to connect the dots? So
Not off the bat. I know what you're going for, but my professional background in space weather also makes it, really interesting for me. But that familiarity is really limited to Earth, its magnetosphere, and its atmosphere. So I don't know directly how you would necessarily try and make that measurement on Jupiter with the helium-3. What was it? Helium-3?
yeah,
Or
H3.
H3 plus?
So 3 helium, like not H2 is a molecule, so H3 is a molecule, and H3 plus is the ion of.
Ah, okay. Yeah, so
Uh,
I would have to look into that a little bit and see what optical bands are available. I certainly know from the literature very tangentially that, there are occasional imaging measurements there of those bands. I just don't know where they lie spectroscopically.
yeah, and even, I mean, there's that, trying to get to H3 plus directly, but the other thing is, you're studying the deeper atmosphere where the energy is coming.
Yeah.
Right. And so is there just some easy way or harder way to have a GCM or something where one of the parameters is the temperature? And so the
So
more roiling and toiling of the, or just what is the root mean square of roiling and toiling, and would that imply a higher temperature in general that would then propagate it up?
I'm wondering if we could look at some photochemical or some electron precipitation catalyzed reactions that might be proportional to temperature and result in changes to hazes at high latitudes. There would, I'm sure, be a timescale delay there that would be significant, though.
Okay, well, anyway, we don't necessarily need to spend too much time in this context on that, but that I wanted to
Yeah.
put the bug in your ear, and Glenn is a good person maybe to talk to about this now that.
Yeah.
The thing I'm excited about is having a data stream that's telling me about what's going on in Jupiter's atmosphere,
Mhm.
as deep as you can see, or deeper than you
Yeah.
expected. And that's where the energy is coming from. That's where the weather is that propagates up and ends up heating the upper atmosphere.
Right.
Or the other way around, like some people think, right, you get the aurora heat, the upper latitudes, and then that propagates heat down the lower latitudes. Although
Yeah, I'll say one of the things that was really interesting from the space weather perspective is how much planetary waves in the neutral atmosphere propagating upward actually can drive ionospheric disturbances. So there's both the bottom side and top side drivers.
right. Okay. But again, I reiterate the exciting thing about your work is time. You know, you don't get one data point every 3 years or something like that. You get 20 a night.
Right.
That's
Yep.
that's critical for study and then integrated over years. And that's the domain that I'm into, and I have a question or a hypothesis to check.
Right.
About it. So, okay.
Well, I look forward to our meeting in August.
Yes, I am. Amanda, I'm installing my son at Boulder. He's going to be a freshman.
Oh, okay,
Yes.
cool.
It's a software installation because he'll be majoring in software engineering.
Okay. Hey, I'm going to stop the recording
Okay.
for now. Well, while we're recording, thank you again very much, Stephen. This was a great presentation, and so we appreciate the time. And thank you for allowing us to record it, and we can all go off and watch it too.